Great. So thank you so much, and thank you to the organizers for inviting me to give a talk here. So this is also interesting in the sense that this maybe provides a slightly different picture. And I'm sad to say there won't be much relativistic stuff in this one here, but there will be some gravity. So in this one, I will talk a little bit about research that I started during my PhD and have been sort of building on since then. Gravimetry means the sort of measurement of gravity. Usually that's just gravitational acceleration. And then we have nonlinear and optomechanics here. And I hope for those who are not super familiar with this to provide a bit of an introduction for each concept. And also to talk a bit about tools that we use when we want to ask things like how can we measure gravity? What is the fundamental sensing limits to gravity measurements? Okay, so my name is Sofia, and I'm here doing a WINC fellowship at Mercury. Let's see. Okay, so what is precision gravimetry and why do we care? So first of all, for example, we have this gravity map here of the Earth. So here you can see deviations from some standard median gravity or average gravity field. And what you can do with this is you can sense, you can essentially see where you have these gravity anomalies. And this enables you to do things like track things you couldn't normally track very well, like meltwater, which you can't really see, for example, from space. So this was made using a satellite from space. And it allows you to, for example, track the mass of water as it moves around. On the other side, so this is very sort of technological application. On the other side of things, we're very interested in, for example, can we measure the gravitational field of really, really small masses? Because this would allow us, if we could actually push this all the way down to where we have masses that are in superpositions, that could enable us to start asking questions like, what does the gravitational field of a superposed mass look like? Which we don't actually have the answer to. So I don't sadly have the reference here, but this was work done in Vienna just a few years ago, and they measured a milligram mass, which is the gravitational field from a milligram mass, which is the smallest mass we have measured so far. And then also we have things like, gravitational wave detection, which really allows us to probe very fundamental aspects of physics and has opened up a new way to actually do astronomy and cosmology by detecting gravitational waves. We also have the notion of modified gravity theories. So there are certain problems, for example, the cosmological constant problem, the predictions from GR and quantum field theory are very, very different. And in this sense, some of these modified gravity theories, they propose ways to solve this problem. So I'm by no means an expert on this, but here you can see a bit of a zoo of all of these different proposals that have been put forwards for how we can modify gravity while still retaining some of the observations that we have on sort of solar system scales. And the question here is, if we can measure gravity extremely precisely, could we rule out some of these or all of these worst case scenario theories that help us solve these problems? And the way we want to try and measure gravity is through something I call, in this case, optomechanical systems. So here's a picture taken from a lab in London at UCL. And this here is a levitated nanosphere. So this is levitated against gravity in a Paul trap, which means you have some rotating electric fields. And this is being illuminated with a laser. So these particles are usually super, super tiny. They weigh maybe 10 to the minus 15 kilograms. And what we're going to use them for is we're going to use them as sensors, and we want to measure gravity with them. So just a little bit of what are the ingredients that go into this. So optomechanics, opto means light, mechanics means mechanics. And we need some kind of mechanical element. So in the case I just showed you, that was a levitated particle. But we can also have other things like mirrors and clamp systems, membranes, and so on. And then we need some kind of probe system or a cavity mode in the case of a confined system that actually interfaces with this mechanical element and which allows us to read it out, because we can't usually, we need some other system to act as the detector onto the mechanics. And when we put these two together, we get the most massive quantum systems that we have in the laboratory. And this opens up quite interesting questions. So one of them is what I mentioned before, can we put these systems in quantum superpositions and measure the gravitational fields from them? That's a really interesting avenue. We're going to take the other route and ask, if we use these systems as detectors, how well can they help us measure external gravitational effects? So here, the system is just a probe, it's not the source of the gravitational field. And the optomechanical, as I mentioned, they come in many different sizes. So for example, here to the left, we have some membranes and clamped systems here. Here we have these levitated nanospheres, and this publication here was the first to show that they can be ground state cooled. Here we have two drum systems which were entangled, so we are starting to see really interesting demonstrations of quantum control of these mechanical systems. And then here finally we also have a superconducting levitated systems which can reach very high masses and a very sort of low noise systems. So this is really exciting. We have quite a plethora of different, a large variety of different platforms, and all of them have different advantages and disadvantages. And I'm not going to, but lucky for us, if we do theory, most of these can be described by exactly the same equations, and that's what we're going to do now. Okay, so how do we interface light and matter in this way? So we're going to go to second quantization and describe them more or less, so confined harmonic oscillator systems. So in this case, we have here one of the simplest optomechanical systems. So we have a cavity with a moving end mirror. So we put one of the sides of the cavity on a spring. And as we shine light into the cavity, the light pushes onto the mechanics, onto the mirror. And that in turn changes the resonant frequency of the cavity. And that changes the way the light behaves. And to lowest order in the interaction here, we can write down the following Hamiltonian that decides the dynamics here. So basically here, this B dagger plus B, that's your X, that's your position, center of mass position, and A dagger A is the number of photons. So the number of photons displaces the mirror, which changes the resonant frequency of the cavity. That's the kind of intuition you want to keep with you. This kind of dynamics of these systems, this was solved back in the 90s, in 1997. There were two papers that looked at these, if you have purely quantum systems, what happens because you solve the dynamics, and they show that you get these really interesting cat states of the light. You can also get cat states of the mechanics. And the key thing, just lingering a little bit here, is that here we have three operators multiplying each other. So we had before, Robert was talking about linear Hamiltonians, linear interactions. In that case, you only have two operators multiplying each other, and then the equations of motion become linear. In this case, that's not true. So we have three operators, and that means that the equations of motion, they become nonlinear. So we often talk about nonlinear dynamics in this case, and that's where the nonlinear optomechanics comes from. In many cases, to describe experiments, you then go on to actually linearize these dynamics. You drive the optics very hard, and that gives you easier mathematics. But we want to stay in this regime, A, because it's the fundamental regime, and B, because we actually see some sensing advantages in this regime. Okay, so that is, we've talked about the systems that we have. So then what tools do we use as theorists to talk about quantum metrology? So then the question is, how well can we measure something, an external effect like gravity? How well can we use our quantum probe, our quantum system, in order to do that? And what we want to introduce here in this case is something called Fisher information. So there are many ways to talk about quantum metrology, but if you want to capture quantum effects, the Fisher information allows you to do that. So it's a bit, the definition is that it's a measure of how much the state changes, how much information you can get from the state as it is affected by something external. So here we have this I of theta. Theta is the parameter we want to measure. It is an integral over these conditional probabilities. So given some measurement outcome x, the probability of measuring some measurement outcome given, or also based on the value of your parameter, is given here. And it has this sort of unintuitive form, but it comes from I believe, like taking the variance of the score, which is, or taking the score, which is something like the variance of the maximum likelihood. So you can, if you look into fundamental notions of estimation theory, the quantum Fisher information drops out as a very natural measure. So in our case, these probabilities, they're given by quantum measurements. So we define some P over M, there's pi x. It can be continuous or discrete, so the x are measurement outcomes. And our state has encoded somehow the parameter theta that we want to measure. So how you encode the parameter depends a little bit on your case. In our case, we'll do it through dynamics, but you could also do it through like gates or operations. But this is the classical Fisher information. We do quantum science, so we want to go quantum. What you could do here is you can say, okay, fine, I have one quantum measurement, but I could ask, what is the best quantum measurement? If I then optimize over all possible measurements, I get what's called the quantum Fisher information. And for pure states, this is quite a nice expression. We just differentiate the state, which depends on theta. We differentiate it with respect to theta, and we compute this quantity. If you have non-unitary dynamics, things get hard. That's it's a lot worse to deal with this, but at least in this level, it's very, very nice. And what really is the key property of the quantum Fisher information is this relation to the Cramér bound, which actually relates the Fisher information to the variance of your parameter. And here, the intuition here is that the variance of your parameter, you want that to be as small as possible, because you want the same value all over again when you measure. And so this M here, this capital M, that's the number of measurements you perform. So if you had infinite time and infinite funding, you could take this to infinity and you still get zero variance, but we never have that. So we want the Fisher information to be as large as possible. So a lot of quantum metrology, the goal is to compute the Fisher information, find the optimal measurement, and then see what is the fundamental limit that you can have for your variance. So just to give a little bit more intuition, the Fisher information can also be seen as a measure of change. So if you take your initial quantum state and you say, when affected by this parameter, it would evolve here. But if, for example, gravity wasn't present, it would go here. The quantum Fisher information is basically the distance between the two states. So to some extent, it's related to state discrimination. And I also wanted to connect this a little bit with some words or phrases that people throw around a lot in this community. And one of them is the standard quantum limit. So this appears a lot when you talk about gravitational wave detection. And here the standard quantum limit is basically a classical limit. Because you can see a lot of works that say, oh, we go beyond the standard quantum limit, we break the standard quantum limit. And that's very nice in the sense that the standard quantum limit is always proportional to 1 over n, where n is the number of probes in your system. So say you have a very strong laser beam, you have n photons in that, then that's the standard quantum limit is set by that. And it's always a balance of what is measurement backaction noise and shot noise, essentially. And shot noise has to do with the fact that photons have intrinsic uncertainty. And measurement shot noise has to do, or measurement backaction noise has to do with the fact that when you measure the system, you disturb it. So if you measure position, you give it momentum, which then also changes position and so on. So the standard quantum limit is set by the sum of these two. And in order to break it, you need quantum resources to do so. You need squeezing or you need entanglement. This should be contrasted with something called the Heisenberg limit. So people often talk about this as well in quantum metrology. And when sometimes they say we break the Heisenberg limit, and that is usually not correct in the sense that the Heisenberg limit is a hard limit. It's set by the energy of your system, and the more energy you have, the more this limit changes. So if you increase the number of probes in your system, the number of qubits, if you change the Hamiltonian, this limit also changes. And this is where having access to nonlinear dynamics is quite interesting, because I've written here, nonlinear interaction contain more energy. I thought about that and then I uploaded the slides and then I didn't have time to change it. So not necessarily correct, but the energy eigenstates scale differently, higher, with the number of, for example, photons in your system. So your energy levels are different. And what happens here is that when you then compute the Heisenberg limit for this kind of Hamiltonian, then you get that this is proportional to 1 over n squared. And that should be contrasted with 1 over n in the classical case. So here we also have this like nonlinearities are useful for sensing. But only certain states, only really quantum states, like superpositions of Fock states here, will achieve this limit. So it depends both on your Hamiltonian and on your states. Cool. So we now have some tools. We have quantum metrology tools. So in the last bits here, I'm just going to go through what we have done a little bit here with these, considering the fundamental sensitivity of measuring gravitational acceleration. So here, let's take our optomechanical systems. Let's plop the Earth next to it. This would be like, say, you have your system that's horizontal and then you flip it, so it feels gravitational acceleration. And to first order, we can just approximate this as mgx. And we can add that into the dynamics of our system. And then the question is, we encode this g, that's what we want to measure, we encode that into our system. And it couples through the mass of the mirror here. So the larger the mass, the stronger the coupling. What our question is now, how do we compute the fundamental sensitivity of this? So we can also do, instead of the Earth, which might be the static, it's always hard to measure, we can instead take a golden sphere, for example, like a really heavy material, and we can shake it next to the system. And in this case, we get a time-dependent coupling, which looks like this. And here we have the distance and so on between the sphere and the system. And how do we do this? So we use a Lie algebra method, because this is nonlinear dynamics still. This is harder than using, for example, phase-space methods. And I'm not going to go into that. But basically what that allows us to do is to decouple the evolution operator into different exponentials. So what this allows us to do here is it gives us a recipe, and just to go through what the different terms here mean. So this here is this nonlinear Hamiltonian that I showed you, the self-Kerr interaction it's called. Thank you. These two terms here encode gravity, and these two terms, they encode the optomechanical interaction. And what we can do with those terms is that we can basically compute this quantum Fisher information conditioned on measuring little g. We find that it looks a little bit like this. This is not super intuitive, but we have some derivatives of these coefficients that we derived. And at certain times, we have some nice decoupling of the system, and we can basically look at this variance of g, and we find this expression and tells us some experimental parameters. The interesting bit here is this delta A dagger A. That's basically a variance of the number of photons that you have in your system. And here, if you input a squeeze state, then you do quite well. A coherent state will also do well, but not as well. And the most exciting state you could put here would be a Fock state, which then satisfies this Heisenberg limit. But creating really good Fock states is very hard. So just to show you some numbers, so here we computed two different sensitivities. These numbers are for a levitated system. But if you increase this mass here, you could also increase this a little bit. And to compare, I think 10 to the minus 9, 10 to the minus 10, 11, that's what you could do now commercially. So what this shows here is that you would have to amp up these parameters a little bit if you wanted to fundamentally do better. So now this is without noise. So that means that if you had noise, this would be worse. And so that's always something that's always more layers to it, the closer you want to go to experiments. I'm going to very quickly just show you also, we can then ask questions about what about modified gravity. In that case, we have a Yukawa-like change to the Newtonian potential. We have this alpha and lambda, and they are very small parameters that change the shape of your Newtonian potential. These are the current bounds of alpha and lambda. As you can see, it's very hard to constrain here where you have very small things. In our case, we can compute that if we say, okay, we just want to measure gravity really precisely. We find these bounds here, where in this case, We also look at if you have a sort of finite size of your system, what does that do? In this case, we looked at a specific theory called the chameleon theory, where matter shields this additional modification to gravity. We also imposed these existing bounds onto these new ones that we found, the yellow and the orange arrows. In this case, we do quite well, but in this case, we found that even if we push the parameters quite a lot, we don't do super well. So we would also have to increase the experimental parameters, so engineer them to be better in order to do much better in this case. Here we do quite well because we assume a very pure vacuum in these systems, which can be done. But the mapping from here to here, even if there is one, it's quite non-trivial. And then finally, a sort of next step. So all of this has been without noise. And the current effort has been a little bit to try and say, okay, so we have light that leaks from the cavity. We have noise that affects the mechanical element, where we couple the position of the elements to some noise modes. Can we import these? Can we solve the dynamics still in these conditions, and then compute sensitivities in these less than optimal cases as well? So with that, I'm not going to read out the summary because I think I'm basically out of time. Yes. So I want to thank you for listening, and I just also wanted to mention that we've just written a review on testing these gravitational effects with massive quantum systems. That's currently on the archive, and we're really keen to get feedback on this. We especially want it to be accessible for students and people who are new to this field. And this RQI crowd seems like the perfect crowd to ask for this feedback. So if you have any pointers for us, we'd be very grateful to hear them. Okay, thank you.
Excellent. Are there any questions for Sofia?
So you set bounds to how good you can measure, but what is it that you actually measure?
Yes, I didn't go into that very much. So in this case, we computed the quantum Fisher information, which means that you're just saying there is some optimal bound on these, and we can compute that, but it doesn't tell you which measurement is the optimal one. So when we looked into it, we found that doing a homodynamic measurement of the light satisfies this bound under certain conditions. For example, you needed systems they entangle, so light and mechanics entangle, and then they decouple. And this kind of decoupling entanglement method, it only happens in certain circumstances, like how strongly they couple. And under those circumstances, a homodynamic measurement is the best measurement because it measures phases. And the gravity is essentially imparted on to the light as a phase shift. So that is a very good question. But for better measurement, that is still to be discovered, I think, yeah.
Do we have one more question, maybe? A quick one? No? Okay. Oh, yes?
Yeah. So in the previous talk,
Yes.
we heard about coupling relativistic systems to non-relativistic one. So this is, of course, coupling a relativistic system to a non-relativistic one.
Yes,
That doesn't make any difference for the energy, the energies you are working with.
No, so I would say that everything here would be very non-relativistic in the sense that if you started to look at really super high masses or curvature effects, you would have to do additional approximations. There's also the subtlety of using the Schrödinger equation, which is what we do here. So if you wanted to do properly relativistic, you would have to go Klein-Gordon, describe these systems as fields rather than that. So in order to use the Schrödinger equation, we need to stay in a single inertial frame where time is well defined. Yeah, so that's definitely, you could add curvature, for example, here as sort of additional perturbations to the Hamiltonian, but you would have to make sure that you stay in a single frame to perform your measurements. Yeah.
But the effects will be beyond your accuracy limit.
That would have to be determined, I think. So you could add second order terms into the Hamiltonian, and then you can ask, if you then evolve the dynamics, you can ask specifically how sensitive would we be to not just acceleration, but also curvature, like the gradiometry, essentially, the difference in acceleration. Yes. So no, that's a very interesting question, which would be nice to to extend this framework with. Yeah.
Let's thank Sofia once again.